Okay.
Hi, you had a 40-minute limit, it seems.
Yes, yes, yeah. So,
Okay.
okay. Okay, is it good? Can you hear me?
Yeah, I can hear you.
Okay.
Everything's
And you
fine
can
as
see
far as
me,
that.
right? Yeah.
Yes, and I think the
Okay.
people are coming back. Yeah.
Yeah.
All
So,
right. Well, I mean, I could have sent you my link, but all right, which doesn't have
yeah.
such a limit. Sorry.
Yeah, I'm sorry. I had the IT department, but something happened. But yeah, my
Uh,
apologies for that. So,
okay, so what was I saying? You were discussing social media.
media, yeah, there are so many
Yeah.
people, and who they can say anything they feel like saying, and and I don't understand because people are using science and the things which are given by physicists all the time, and still they think that physics is or science is not important or uh,
Yeah. Well, I would say, yeah, that is a problem, and you have to be careful uh, and form your own judgment of what's being said out there. But it is also a very powerful tool for physicists, not only to communicate with each other and to get a sense of what's exciting that's happening, but also to communicate with the public. And yeah, definitely scientists should engage with it. I mean, you can't just say
yeah, because I see many
that's
scientists on social
yeah,
media.
that this is that's turn up their noses and say this is beneath me and I'm just going to publish in this journal.
Yeah.
That's also not right. I think it is the new world, and scientists should be part of it. And there's no turning around, and it's very powerful. I couldn't be talking to all of you if it wasn't for social media.
Yeah.
So it is very important and very useful. Yeah.
So, uh, okay, so a few years ago, I had the privilege of speaking with Professor Weinberg, Nobel laureate in
Mhm.
physics in 1979, alongside Sheldon and Salam. So he shared with me the deep passion Salam had for establishing an institute dedicated to theoretical physics and mathematics in one of the developing world countries. Now,
Yeah.
unfortunately, those in power at the time dismissed the idea, arguing that basic sciences held little or no value. So, this lack of support ultimately led him to establish that center in Italy. Given this context, what do you think are the reasons why developing countries still fail to understand the importance of basic sciences?
Um, what did- well, I guess people see other things as priorities, but especially when you're a poor country where there are many other needs. Uh, I think that'd be the short answer. But but I think different countries have taken different routes. If I, were to compare, say, India and China, uh, I think China, they had the Cultural Revolution, which in fact was terrible for essentially all academics. They were forced to go and work in the countryside for a long time. It destroyed a whole generation
Mhm.
of academics in China. Uh, okay, so that was terrible start for China. And then
Mhm.
China has since then focused initially on primary education of
Mhm.
everybody and been very successful at that. And now it is in the last 10, 15 years focusing on research institutes and wants to be, at a leading research country. And it's very quickly becoming that. So it was a very complicated route, but it's remarkable what's happening now.
Mhm.
I think in India, uh, there was, I think Nehru himself, I think, uh, was very much in favor of developing science institutes. And, there was the Indian Institute of Science in Bangalore that had been functioning for a while. And then he promoted the formation of the IITs and then the Tata Institute in Mumbai. So these places were funded, very generously, at least for a while, and they grew. And now, of course, uh, India has changed changed country. I mean, the science has come a long way, and you can, many institutes and many leading conferences and leading research is done in India. So it's really been amazing to see all the changes in my lifetime in India. But at the same time, you could say, India is still behind China in primary education. There was a missed focus, I think, which now is becoming more important. And, now finally the literacy rates are approaching rather high levels, at least in many states. But it took a while for that to happen. And you could make the case that India should have not done it that way. Well, I don't know. That's looking back. And that it should have focused on primary education more in the early days. But that's, but anyway, we were talking about Abdul Salam. I went to his house in London. His son, Ahmad Salam, invited me and my wife Usha there last year, and he still preserved his study and his chair in his house, and all the papers. And so it was a real honor to be there. And I think, so Salam, of course, as you said, formed this ICTP Institute, and that's had a huge impact, I think, on science of the developing world, as I'm sure you know. I've met many scientists from all over the world there, and it has helped set up institutions. I think they're working with Vietnam now, in Brazil, many places in Africa. It's really bringing science up to current times. So I think that's a very important mission. So I think ultimately, I think Salam put it very well. Science is the common heritage of mankind. And it is true that the Europeans dominated science from 17th, 18th century, but that was not always the case.
Exactly.
Many, and that's becoming clearer now from many people looking more carefully at ancient documents. There were a lot of developments in India, the greater Indian subcontinent and the Middle East. And for many, especially in mathematics, where this area was leading the world for quite a while. And so now it's time for us to catch up.
Exactly.
Yeah.
Okay, now let me ask some questions related to string theory and your research. So we have a string theorist with us, Professor Azim. He has just joined IPA. So let me first ask one question, and then I think Azim can ask questions. So ADS-CFT is a concept that emerged from string theory, and it primarily works in highly symmetric situations. So do you think this framework can actually be applied to condensed matter systems? And can it become a useful tool in this context?
Sure. Well, I've written a book on exactly that question. So I would say, so what is ADS-CFT, just for the uninitiated? So it's a way of relating gravity, quantum gravity, or even defining what quantum gravity is in certain negatively curved spaces to ordinary quantum mechanics of many particle systems. And so it's also what we call a strong-weak duality, meaning that if the gravity theory is easy to solve, then you learn something about a many particle system that's not easy to solve. And that's one of the reasons I got interested in it. I wasn't particularly interested in gravity or black holes or anything, but I was interested in many strongly interacting many-body systems, especially the role of quantum entanglement in determining properties of quantum many-body system. So that's a very, very difficult problem, and I was happy to use any tools that can advance it. And ADS-CFT was one of those tools. So ADS-CFT tells us about certain entangled many-body systems. Now, those entangled many-body systems it tells us about, these conformal field theory, CFT, are not the ones that are really directly relevant for any important question in condensed matter physics. I mean, they are kind of very specialized questions as far as condensed matter physics is concerned in particular. But the point was that, just having an example of some understanding of a strongly entangled many-body system and what it does can be a very useful learning tool. I mean, I sometimes make an analogy to what happened in the study of one-dimensional systems. So some of you may know in one-dimensional systems, there are so-called integrable models. Now, they're very special. No real system in the world is actually an integrable model. But knowing about integrable models and generalizing that to other systems was very important in the history of our understanding of one-dimensional quantum systems. So that's the sense in which it was very important. ADS-CFT was a powerful tool. It or maybe continues to be. It gave us an insight, a new way of thinking about very strongly interacting many-body systems. And it was at that time being applied to CFTs. And it was while I was studying some of these properties of these CFT and their dual gravity theories that I realized actually some of this behavior is very similar to what's now called the SYK model, which was not a, which is some sort of CFT, but it's a model defined using electrons. It's just very simple to define. I can define it to any undergraduate student in quantum mechanics. And then it turns out that there's also a duality between SYK and certain black holes. And that's turned out to be very powerful. In this case, I guess I can somewhat proudly say the knowledge went the other way, where from knowledge of quantum matter, we have now learned more about black holes. And so that's been very satisfying. It's been a two-way street. So I think it's always, when you're dealing with a very complicated system, it's always good to have more and more examples of some corners which are of the space of systems you want to understand that are well understood. And ADS-CFT is one very important influential corner like that.
Okay. So, Azim, do you want to ask a question?
Yeah, okay, yes. First of all, hi. Thank you for being here. And so in preparation for it, I read an article by you, which is kind of, I think, more colloquium style and titled like Strange Metals and Black Holes, so the relations between them. And I think it's a very fascinating fascinating article. And I will, so my questions will come from someone who's kind of, I think you mentioned that in this case, the knowledge went from condensed matter physics to theoretical particle physics and string theory. And I think
it was a two-way street, and both things have happened. Yeah.
but I think we are kind of envious in quite a few respects of like with the things that come up in condensed matters now, especially I think especially about the topological aspects of quantum field theories, in which I feel like condensed matter physics has taught us a lot. So what do you think of like that general framework and how it came about? So I think like, maybe you can give us a general overview.
Sure. This is not connected to ADS-CFT as such. So you're talking about topological phases of matter, where where there's a different sort of entanglement, which leads to these particles that have very strange braiding statistics and so on. Yeah, so that's also a very fascinating story. I mean, there were many different inputs. You could say that it was really experiments, and the discovery of the fractional quantum Hall effect that really got people taking this topic very seriously. But also there was, independent of experiment, there were these amazing papers by Witten on Chern-Simons gauge theories, which introduced many of the ideas that eventually were applied in condensed matter systems. And then, with these, I think this all happened around, mid 80s, late 80s. And since then, there's been just an incredible development of different types of topological states of matter, different types of fractional quantum Hall states, and then there's spin liquids that I have worked on. And there were some pioneering ideas by Phil Anderson in 1972. And so all of that came together in the early 90s, and very many people working on it, and also many experiments. And it's continuing this day. And you could say that its biggest impact, maybe in the future, is on quantum information theory, where people are using ideas from topological phases of matter to build quantum error correcting codes. The recent claim by Google of using the surface code to have a fault tolerant qubit is very much coming from this theory of topological phases. In fact, in this case, a phase that I discovered with Nick Reed in 1991 was called the Z2 spin liquid. Sorry for that short commercial. But anyway.
So I went off on a tangent about something I'm very interested in, but let me course correct now. So reading your article, so one thing you mentioned in that in order for SYK model to match the entropy of a black hole, what you need is something called many-body quantum chaos. So what is this many-body quantum chaos?
The idea of quantum chaos was introduced by Steve Schenker, Mon Maldacena, and Douglas Stanford, but it's very much related to things I was talking about earlier, many years earlier, which is, we would say, thermalization. If you take, well, first of all, there's classical chaos, which everybody knows as the butterfly effect. And there's some analog of it in few-body quantum mechanical system, having to do with statistics of energy levels. But many-body quantum chaos is slightly different, and it's much more analogous to the original butterfly effect of classical physics. And you could relate it in terms of thermalization. That is, suppose I take some system in a box, many-body system, and it's in some state that I prepared very carefully. I put it in some particular quantum state, and then I let it evolve in time. And for almost any system, if you wait some time, if you look at a small part of it, some subsystem, and you look at any observable you want, various correlation functions in that subsystem, they will be indistinguishable from the Gibbs state, from a thermal equilibrium state. So this is called thermalization. Any quantum system sufficiently generic will eventually look thermal. Okay.
So
there's no proof of this, but there's a lot of... Huh? No. So I'm not decoherence. People talk about taking a system and coupling it to a measurement apparatus, and then there's a decoherent. But that's, then you're introducing this measurement apparatus that's introducing its own complications. And so I don't like to think of it that way. I just take a system in a box. Everything is the universe. The universe is a box. There's no observer. That's it. There's just the universe, and it's moving forward in time. And the only thing I'm doing is just looking at a small part of it. That's it. Just pick any part. Need not have to be that small, even half of it. And then I look at observables, and it will turn out, because of chaos, essentially, that system will look thermal. It will have thermal correlation functions. And so this is called eigenstate thermalization. Okay, so it's a hypothesis, never been proven. It's probably really, really hard to prove. But a lot of evidence is correct. All of physics relies on this being correct. So then the question becomes, how quickly do you become thermal? So how quickly do you become chaos. So what's special about SYK and black holes is they're champions of chaos. They become chaotic as fast as possible.
Yeah.
And so, I mentioned Schenker, Stanford, and Maldacena. So they came up with a very precise criterion on how to measure
I have got a question.
the onset of chaos. Yeah. Okay. Yeah, go ahead. Yeah, that's pretty much all I
Sir,
wanted to
I
say.
have got a question. Sir, do you explain what is the universe? Universe is expanding, and there is a concept of parallel universe, multi-universe. Can we understand the universe? You know that there's a lot of infinite particle existing in the universe. So can we, able to understand the universe in future, or looks like complex structure? Bit by bit, it is extending, and lots of particle within points in the universe. Multi-universe concept, parallel universe concept. Even we can't understand the universe still. So what is your idea
yeah,
about this?
maybe let me try to summarize your question best I can and answer what I can. Can we understand the universe? Well, that's what physics is about, trying to understand the universe. And it does. Why it also depends a bit on what you mean by understand. It writes down some simple description, Einstein's equations or whatever, and from that simple description, it makes certain predictions. And the predictions are tested, and in many cases they work spectacularly well. But do you mean that's understanding? So why is the universe obeying Einstein's equations? I have no idea. This is just a fact that we work with. Now, but if you then ask further questions, which I might call metaphysics, which is, like the question I just asked, which is, why is the standard model a standard model? Why is gravity the way it is? Well, people try to understand
Sir,
that
what
at a
about
deeper level.
parallel and
using
multi-universe concept?
Yeah, I'm coming to that. So when you try to understand it using, ask the further why does the standard model have its structure? Why does various coupling constants in the standard model have certain values? Then they have proposed the idea that this may be because there are other universes. So this is an idea. It has nothing to do with my effort to understand the universe given the laws that we think it obeys. It's really asking, well, where did the laws come from? Well, I don't know. And this is an interesting idea. And ultimately, if they make some prediction that can be tested, then I'll be more interested. But at this point, it's mostly speculation.
Sir, I have a question.
Yes, please.
I want to ask you what new mathematical or conceptual framework do you think will become important? Are there any theoretical tools that you believe hold promise or something? Hold any potential of some kind for physics?
You are saying, I'm not sure I understand you.
What I'm basically trying to ask is, what conceptual frameworks do you think mathematically hold promise for physics in the future whatsoever?
Well, okay. That's really hard to say. I mean, I would say, these days, learning quantum mechanics and statistical mechanics are, extremely important, not just in physics, but in computer science, machine learning. These are the basis for many, many things. A mathematical framework. Yeah. If you ask, what field of mathematics I wish I knew more, I can only say, I would say I wish I knew a little bit more of statistics and a little bit more of, some aspects of algebraic geometry that seem to be quite important these days for topological phases. But yeah, mostly, but as I said earlier, if I'm facing a question in mathematics, often the most efficient way is to be clear about the physics and then talk to some mathematics friend who can help you.
Azim, do you have any more questions? And Babar, Dr. Babar, do you have any more questions?
You're muted, Azim.
Oh, Am I? Let me just.
Azim is muted. No, you're
Oh,
okay,
yeah,
Shabana.
Azim is muted. Let me ask you.
Okay.
You got again muted.
Yeah, just give me a second. Yeah, here you go.
Oh, okay. So maybe like one last question, which I feel like the answer might be it's hard to know, but so you mentioned this proof by like Maldacena and Strominger. So they at least, so in 5 dimensions we can actually for like very special black holes, we can actually kind of compute their entropy by
So that was, I didn't mention that. That was Wafa and Strominger. Yes, the 5
yes,
dimension.
yes.
Yeah, correct.
Yeah,
Yeah.
so yeah. So Waffen
Or so,
like in 5.
yeah.
So yeah, so you can. I mean, the paper is mentioned in your article. So yeah,
Okay.
so they have this proof that for like certain special black holes in 5 dimensions, we can actually kind of compute the entropy from first principles, which I think like kind of like extremely fascinating result.
Hmm.
And I think like an SYK model I feel like it does at least give us some clarity in maybe like 2 dimensions or one uh where it's dual to where it's dual to some theory of quantum gravity. Do you think like we can have something similar in 4 dimensions?
We
Or
do. I mean, so this is the thing that there's some very nice papers, especially by uh, Turiachi and collaborators recently on all of this. So the Strominger-Wafa result is, they gave what I call the BPS state. They counted the
yes.
BPS state, which are the zero energy ground states.
Hmm.
Now, however, that's a very special structure for black holes that
Yeah.
have low energy supersymmetry. But
Yes.
what SYK and supersymmetric SYK has now taught us is what happens not just at zero energy, but at finite energy in 4 dimensions. So for generic
Okay.
black holes in 4 dimensions, we now understand the structure of the density of states as a function of energy. And without supersymmetry, it's quite different from what Strominger and Wafa found. So their results,
Okay.
one could say, were not realistic because they were about black holes
Yeah.
that have supersymmetry even at zero energy. Which okay, but for non-supersymmetric low black holes, we don't have a full exact solution the way Strominger and Wafa did,
Yeah.
but we can still compute the low energy behavior quite accurately now through SYK techniques.
Okay. And
Yeah.
kind of like the first correct like
Yeah, so I have an
yeah.
article on the archive research for black holes and SYK in the last year where I reviewed all of this literature.
Okay, nice. Okay, thanks.
Sure.
Okay, so let me. Okay, so Dr. Barber, do you want to ask a question or?
Oh, I don't see him here anymore.
Oh, okay.
Okay.
Yeah. So okay. So let me just ask you something in Urdu. अब आपकी उर्दू का टेस्ट हो जाए?
हाँ हो जाए मैं कोशिश करूंगा
ठीक है. अच्छा, आप मुझे ये बताएं कि आपकी क्या एडवाइस है उन लोगों के लिए, स्टूडेंट्स के लिए, यंग लोगों के लिए जो फिजिक्स करना चाहते हैं?
मैं कहूँगी जरूर करिए. बहुत अच्छी तैयारी है, बहुत सारी चीजें करने की आपके एजुकेशन
Yes,
के
in
बाद.
English. That was
नहीं,
perfectly
नहीं.
fine.
मैं बोल सकता हूँ पर सही जगह में होना चाहिए.
That's okay.
Yeah, I mean, अगर इंटरेस्ट है, शौक है तो क्यों ना करो. क्योंकि इंजीनियरिंग में तो एक ही चीज सीखते हैं, वैसे एक नहीं काफी सीखते हैं, पर सब कुछ बदलता रहता है. जब तक आप ग्रेजुएट करोगे तो सब कुछ बदल जाएगा. तो फिजिक्स के साथ तो तुम भी खुद बदल सकते हो, पर बिना इंजीनियरिंग में शायद इतना आसान नहीं होगा।
Exactly. और फिजिक्स की ये है कि एप्लीकेशंस हर फील्ड में है, राइट? एट द एंड ऑफ द डे. So, okay. So let's just move to our last question. You had told me that your parents are from Gujranwala, Punjab, right? And then at
My
some
grandparents.
point, grandparents.
My
Oh, okay,
grandparents,
grandparents.
yeah.
So they moved to, so they moved to some other part, right? Before the partition.
Yeah, so my parents were both born in Delhi. I think my mother, I think it's similar. But both my maternal and paternal grandparents, my dada, dadi, nana, nani, were in the Lahore area. I think my grandfather was from Gujranwala, and my from my father's side, from mother's side, and they're from Kamoki. I don't know.
Okay, that's a small town in Punjab. Yes. Yeah.
So my aunt is still alive. She's 91 or something, and she used to live in Kamoki. I keep asking her. She lives in Jaipur now. What was it like? But she doesn't remember very much.
तो आप लोगों को मौका मिला वापस आने का, विजिट करने का?
मैं कभी पाकिस्तान में नहीं गया। तो मेरे मम्मी पापा तो जन्म तो दोनों का दिल्ली में हुआ था, मैंने कह दिया। पर और मेरे नाना का बोलते रहते थे लाहौर के बाद, पर कभी नहीं गए वापस। वो दो दादा दादी और नाना नानी सब दिल्ली में ही थे, पार्टीशन से पहले।
ओके,
काफी साल पहले दिल्ली में आ गए थे।
ओके, सो या
तो आप कभी इंडिया की सैर की है? कभी
नहीं,
नहीं गए?
कभी भी नहीं।
अच्छा।
Never.
तो आना चाहिए। तो वीजा मिलना मुश्किल है?
I have no idea. I have never applied. Yeah. Yeah. So thank you so much.
Thank you, Shabana. Yeah.
Yeah. No,
I think
seriously.
Mr. Babar Qureshi is back. You know.
Oh, okay. Yeah. Let's just ask if he has a question. Dr. Barber, do you have a question?
Yeah, I can ask a question. I was just getting in and out my Zoom chat. So let me ask a very general kind of question. So coming from high energy theory, like there is this kind of criticism of the theory that it has gone way too far away from the standard model, and what you are doing is not really related to what we see in the experiments. So is there such a tendency which you can say that it's also present in condensed matter physics, that you keep coming up with new phases which we probably never gonna see in real systems? And on the other hand, I don't know the current status of the condensed matter, but there are, for example, how much progress has been made in explaining superconductivity at high temperature compared to what we already knew, let's say, in the 80s. So do you have any comments on the state of condensed matter with respect to this criticism on the high energy theory?
Okay. That's a great question. I mean, I think first of all, I don't think, to address the high energy theory part first, I don't think string theorists are wasting their time. I mean, it is still interesting physics. They're learning more about physics in different regimes, even though it may not be directly related to current experiments. And it's hard to predict, 50 years from now, what will be really important. So as long as it's intellectually coherent and asking questions that are forward-looking, I think it's fine if that's how science works. Not everybody should be looking at the latest data. I mean, that's not how, Einstein, when he came up with the idea of entanglement in the EPR paper, wasn't looking at any particular data. So, okay. So the condensed matter, yeah, even today, I think it's become a lot somewhat less connected to experiments than it used to be. There are many people talking about very exotic phases in 4 dimensions and all kinds of things happening. But I think it's still very interesting, deeper understanding in quantum mechanics in its different aspects. So it's fine. And in regard to superconductivity, do we understand superconductivity better today than the 80s? Okay, that's very close to my heart, and I would say definitely. I think there's been a lot of progress in better understanding of, say, the Cupid superconductors and all its complex behavior. But, it's never going to be like PCS theory where you can predict everything and even get all the numbers right. It's a much more difficult problem. But there's a lot of new ideas, a lot of new progress, and one could say it was from thinking about all the phases of, say, high temperature superconductivity that there's been this remarkable progress in topological phases of matter and its impact on quantum error correction. You could take some credit for that in condensed matter physics. Anyway, okay. I've gone on too long. All right. I think people.
I'm just okay. So, do you have any more questions, Azim, Dr. Babar?
Yeah, I can see the time left is 3 minutes. So
Yes. Okay. Yeah, I guess he has a question, just one question. So, would you like to ask?
the questions in the chat.
Oh,
Yeah, I can see
okay.
them. Well, okay, there's I see 3 minutes left, so I will quickly make a few comments. So, how might SYK help us understand more about the structure of space-time at quantum level? Well, I think I mentioned how it's helped entropy of black holes, and I think also this work on wormholes that's helping us understand the page curve of quantum of black holes. That also is based on some insights from the SYK model. The question about the parallel universe, I already said that. Then can you ask about what process goes through his head when he's trying to solve some very challenging problems?
You definitely do.
I don't know. If something is really frustrating me, I give up and I do something else. I go for a walk, and maybe someday in the future some thought occurs and I go back to it. I don't know. And but progress is all. It's you have this view that there's some eureka moment, like Archimedes running out his bathtub or something, where suddenly everything is solved. That's never happened to me. It often, you may have made some real progress, but it's years before you appreciate that you made some real progress.
Yeah.
Okay. Yeah.
So,
all right.
So, okay. We have just 1 minute and 20 seconds left. So if you have a question, you can quickly ask. And we can just,
Yeah, well, yeah, I mean, we are very good towards the end. Let me just, if you could say, in a few lines, how should one think about quantum phases as opposed to the ordinary phases of matter? Because, I mean, quantum forces are involved over there as well.
Yeah, I mean, okay. So this is more a question of terminology, but of course, yeah, quantum mechanics is really important to even understand copper or silver or anything like that. But I think the modern idea of quantum matter is matter in which you have to think about the quantum mechanics collectively with entanglement between many electrons. And I would say we are still at the very early stages of understanding the many phases of matter when entanglement is really important. Yeah. So that's my very short answer.
Okay.
Okay.
Yeah.
I think we're going to be cut off. So
yes.
Thank you very much.
Thank you so much. Thank you.
Thank you.
Bye.
We hope to